All right. Sorry about the interruption there. I was in mid-sentence, and there was a power outage, so I had to go to a different office to resume the discussion. So, as we were saying, we had Fermat's theorem, and we have just demonstrated that at x equals c, in the case of a local maximal point, we've shown that the derivative at x equals c is greater than 0, and also the derivative at x equals c is less than 0, depending on how you approach c. So these inequalities must be true. Both of these must be true, and so we have to conclude that the derivative at x equals c is 0. So this is essentially a squeeze theorem. All right. So we proved it for a local maximum. The case for a local minimum can be proved in a similar fashion. And then there's an exercise in the book, which you can do, but it's not a requirement. So, okay, so now you have to be careful when you apply the theorem. We can't expect to locate extreme values simply by setting f prime of x equal to 0 and solving for x. That would of course be the case of y equals x cubed. Okay, so well, I think I'll probably show you that to you next. But so obviously, if y is equal to x cubed, okay, then y prime is equal to 3x squared. And of course, y prime is 0 at x equals 0, but we know that the origin is not a local min nor a local max for y equals x cubed. So Fermat's theorem only asserts that if it is a local min or a local max, if a point is going to be a local min or a local max, then the derivative at that abscissa of a local min or local max will be 0, but not vice versa. If the derivative is 0, it's not necessarily the value of x that makes the derivative 0 is not necessarily the abscissa of a local min nor a local max. Okay? All right, so continuing on. Yeah, so here's the x cubed case. So as you can tell, we've talked about that. So obviously, again, the derivative right here, f prime of x is equal to 3x squared, f prime of 0 is 0, and so you can see that the origin is not an extremum point. It's actually an inflection point. Okay, it's not a point of transition from increasing to decreasing or decreasing to increasing. Okay. So next slide. Next slide, yeah. And the author goes on to say that so there's a horizontal tangent at the origin, okay? And the graph crosses its horizontal tangent. So if the graph crosses its horizontal tangent, then that crossing is not necessarily a local min nor a local max. Okay. All right. So absolute value function. Now, we know that the absolute value function has a global minimum as well as a local minimum at the origin. Okay. But the function, as we proved earlier, is not differentiable at the origin. Okay, so you cannot set f prime of x equal to 0, where f prime of x is the derivative of the absolute value function. Okay, so so be careful with using Fermat's theorem. Even though you could attain a local minimum or local maximum for some functions, it may not be differentiable at those particular points because of the peculiar nature of the function, as in the case of the absolute value function. Let's see, and here's a warning. Yeah, so we have two cases of how to be careful when using Fermat's theorem. Okay. Yeah, so the theorem suggests that we should start looking for extreme values of f at the number c where either the derivative is equal to 0, the derivative at c is equal to 0, or the derivative of c does not exist. Okay, so in this case, this would cover the case of y equals x cubed, and this would cover the case of the absolute value right here. This is the case. Okay. All right. So, and so the numbers, these two numbers right here, the sets of these two numbers, where f prime or c, makes f prime of c equal to 0, or where c makes f prime of c does not exist, these numbers are called critical numbers, okay? So there are two criteria for critical numbers. Critical numbers are those which make the derivative of the function equal to 0 or make the derivative of the function non-existent, okay? So, so c is in the domain of the function, all right, so be careful now. C is in the domain of the function, but c may not be in the domain of f prime, okay, as in this case. All right, so that's how you hunt for critical numbers. So there are going to be quite a few WebAssign questions where you're going to be trying to extract out critical numbers for a function. All right. So here's an example, an interesting example. Find the critical numbers for this function x to the 3/5 times 4 minus x. Okay, so we go ahead and just use the classic product rule for differentiation. So it would be the first function times the derivative. The first function times the derivative. What happened? Sorry. Looks like my slides are getting a little bit messed up here. Let me try it again. Yeah. The slides are bleeding. Sorry, my slides are bleeding. Let me refresh this. Okay, try it again. Sorry. I'm on basically slide 45, right? Or somewhere around there. Okay, so sorry, let me fix the bleeding of the slides. I'm going to have to get rid of the browser. Yeah, okay, so there we go. I see how it was actually a paste, wasn't it? Okay, technology. This is new stuff, guys. So I have to get used to the manipulating the technology. It's going to take me this semester to get proficient with it. So let's see where we were on the concept of critical numbers, and we were doing an example of calculating critical numbers for a function. So let's go to that page. Okay, so here we were. Okay, so we were back on this page. All right, so now, so we want to calculate the critical numbers for this function f of x is equal to x to the 3/5 times 4 minus x. And so we're going to use the classic product rule for differentiation. So it will be the first function times the derivative of the second. So the derivative of the second function is -1, plus the second function times the derivative of the first. And so we use the power rule for differentiation of the first function. And then what do we do here? We have a sum, okay, negative x to the 3/5 plus this, and then we proceed to add the two functions algebraically. So this is an algebraic addition of these two functions. And then after simplification, the derivative is found to be here. And so now I can tell you what the next slide is going to say. It's going to basically set the numerator equal to 0, and it's going to set the denominator equal to 0, and solve those two equations. We'll get two values of x, which constitute the critical numbers. So yeah, and so here's another alternative. We could write f of x. Okay, so f prime of x is equal to 0 if 12 minus 8x is equal to 0. Okay, or x is equal to 3/2. And f prime of x does not exist when x is equal to 0. So we have two critical numbers. This x equals 0 comes from noting that the denominator is equal to 0 when x is equal to 0. And so 0 is not, 0 evidently is not in the domain of the derivative. Okay. All right, so we have two critical numbers. All right, so let's see. We have this note. If f has a local maximum or minimum at x equals c, then c is a critical number. All right. Okay, so that's the essence here. So we have this theorem. If you have a local max or a local min, then the derivative of the function at that particular value of c is either a local min or a local max. Or I'm sorry, the derivative at the local min or local max will be 0. Sorry. Okay. Yeah. All right. So to find an absolute maximum or minimum of a continuous function on a closed interval, we note that either it is local, in which case it occurs at a critical number, or it occurs at an endpoint of the interval. Right? So on a closed interval, the maximum or minimum point, let me show you an illustration. All right, so here's our coordinate axes. All right, and so here's our, suppose we have a function that goes like this. Okay, so in this case, for this particular function, we have its domain being a closed interval here. So the function is defined at the endpoints. And here, we have the absolute max occurring at an endpoint. And then we have a local max occurring interior to the closed interval. And then we have a global minimum occurring in the interior of the closed interval. Okay? All right, so the maximums either occur at a critical number on the interval, or they occur at an endpoint. All right, so we can now do an extraction of local mins, local maxes, global mins, global maxes on a closed interval for the function. So let's see how that works. All right, so we have a three-step procedure. All right, and so this procedure you'll be required to use in WebAssign assignments. So to find the absolute maximum and minimum values of a continuous function, f, on a closed interval, find the values of f at the critical numbers of f in the open interval. Okay, so we can use Fermat's theorem to do that. Okay, then find the values of f at the endpoints on the interval, and the largest value from 1 or 2 is the absolute maximal value. The smallest value in the smallest value is the absolute minimum. So do they give an example? They probably do. All right, so for instance, f of x is equal to this polynomial, and we want to find the absolute max and min values of the function on the domain -1/2 to 4 inclusive. Okay, so first of all, we take the derivative, okay, and we extract out the critical numbers. So f prime of x exists for all x. The only critical numbers occur where f prime of x is equal to 0, and that happens at x equals to 0 or x equals to 2. Okay, and 0 and 2 are elements of the interval for which we're analyzing this function on. Okay, so 0 and 2 are contained in this interval. Okay, all right. So what else? So f of 0 is 1, f of 2 is -3, and the values of f at the endpoints of the interval. So at the left endpoint, f of -1/2 is an 8, and at the right endpoint, f of 4 is 17. So you have to compare these four numbers. And we see that the absolute maximum occurs at here, at f of 4 is equal to 17, and the absolute minimum occurs in the interior of the interval. F of 2 is equal to -3. So global max, or absolute max on the endpoint, global min, or absolute min, in the interior of the interval. Okay, so this is called the closed interval method, right here. Closed interval method for deriving these extreme points on the graph of the function. So you could have used the closed interval method for your first project, for instance. Okay, had you known about it. All right, what else do we have? Okay, so we said that. All right, so, and here's the graph of the function to verify your results. X cubed minus 3x squared plus 1, you can see there's the absolute max at the endpoint, right endpoint, and an absolute min in the interior of the interval right here. And you can see the absolute min is also a local min because it's a point of transition from a decreasing function to an increasing function. Okay, so what's next? Exact values. So yeah, so you can use the graphing calculator to estimate maximum and minimal values. We've done that. What else? The closed interval method. Okay, exact values. Exact values. All right, so use a graphing device to estimate the absolute minimum and maximum values of the function f of x. Okay, so we can do that. All right. All right, so let's try that. Let's give that a go on the next page. Let me add a page. So we're going to do what he says. Okay. So we'll pull up our class calculator. So this will be www.desmos.com calculator. All right, and so what was the function? It was let's see, what was it? X minus 2 sine x on 0 to 2 pi. All right, so we're on slide 68. So we have y is equal to x minus, I forgot, slide 68, x minus 2 sine x, sorry, I keep forgetting. X minus 2, y is equal to x minus 2 times sine x, 0 less than or equal to x less than or equal to 2 pi. And so let's see, there's the graph. And we want to extract out the absolute min and absolute max on the interval 0 to 2 pi. So let me adjust the window so that the x-axis labels take on this character. Okay. All right. So now we can just zoom in, right? And so the absolute minimum occurs perhaps at this point, and the absolute maximum occurs perhaps at that point. Right, so let me do a print screen of this. Stand by while I pull up the one second. Let me extract out the graph. Okay, so let me go back to the slide. Go back to slide 68. Okay, so if we were to answer the A part of this example, we would have this. Okay, something that looks like this. So there's the answer to the A part. Okay, all right. So now we can use calculus, a less resource-intensive undertaking, to find those values. And so there's the sketch. So they set their viewing rectangle just like we did. And let's see. Oh, I went backwards. 68, 69. Sorry, I went backwards. Okay. So there's the author's sketch, and let's see what he came up with. He came up with 6.97 and x equals 5.2. Yeah, so, and we said 5 pi over 3. So that's what those are his results graphically from the graphical extraction. Okay, and then his local minimum, same as ours. Okay, and so the absolute maximum, oops, why am I going backwards here? Okay, 71. Oh, I see what the problem is. 72. All right, so now, so the alternative part of this question was to use calculus to calculate those values. Okay, so f of x equals x minus 2 sine x is a continuous function on the closed interval 0 to 2 pi. So we calculate its derivative, which is 1 minus 2 cosine x, and then we set the derivative equal to 0. And that, of course, happens when cosine x is equal to a half. So cosine x is equal to a half at x equals pi thirds, or 5 pi over 3. Okay, and so recall our picture right here. Okay, so calculus verifies our selections. Okay, all right. So let's see what it is. And so evidently they plug in the values, pi thirds into the function, and they get the local minimum, the ordinate of the local minimum, and they plug in the 5 pi over thirds, pi over 3 into the function, and evaluate, and they get the local maximum, which agrees with our graph that we constructed. Okay, so the values of f at the endpoints, of course, are, I guess we should look at that. Okay, so we used Fermat's theorem to calculate the local mins and local maximums. Now, using Fermat's theorem, what does that yield? Okay, I'm sorry, using the calculating the values of the function at the endpoints. Okay, so let's pull back our graph. So we need to calculate, identify the endpoint. So here we have the origin, okay, and then here we have f of 2 pi. And so f of 2 pi clearly is below this point, and the origin is clearly above this point. So the two critical numbers we found, the function evaluated at the two critical numbers will make up the extreme points for this graph. We can cast aside the endpoints. The endpoints are not in play for the solution to this particular problem. Okay. And so here they go. They calculate it. All right. And so you compare the four numbers. You compare f of 0, f of 2 pi, f of pi over 3, and f of 5 pi over 3. Compare those four numbers to make the determination of which one is maximum or minimum. Okay. All right, so now we talk about the Hubble Space Telescope. So what's going on with this? What was the problem? Okay, so let's see here. Yes, slide 77. All right, slide 78. So a model for the velocity of the shuttle from liftoff was t equals 0 until the solid rocket boosters were jettisoned at t equals 126 seconds. So the velocity of the shuttle back then was given by this equation in feet per second. All right. So here you have it's a cubic equation. And let's see, what else do we have? So we want to estimate the absolute maximum and minimum values of the acceleration of the shuttle between liftoff and jettisoning the boosters. Okay, so you know that acceleration is the derivative of velocity. So we are asked for the extreme values, not of the given velocity. So we want the extreme values, not of the velocity function, but the acceleration function. Okay. All right, so we want the extreme values of the acceleration function. All right, so what is the acceleration function? So the acceleration, of course, is the derivative of the velocity function. And you just take the derivative of the polynomial. Here it is. And so here's the equation for your acceleration function. So we're going to find the extreme values for this function. Okay. Okay. And so we apply the closed interval method, where we've, on the interval 0 to 126, the derivative of the acceleration function is shown here. Okay. And so the closed interval method means we need to find four numbers. Okay. We need to find, well, let's see, we need to find the value of the function at its endpoints and then the critical numbers. So in this case, the acceleration function is the derivative of the acceleration function, that is a straight line. And so we'll, in this case, for this problem, we only need to find three numbers because there's only one solution for the straight line crossing the x-axis. Okay, so we'll have three numbers we need to analyze: the endpoints as well as where a prime of t is equal to 0. All right, so here they solve the equation a prime of t is equal to 0, and that happens at 23.12 seconds. And then we just analyze the endpoints. So a of 0 is equal to 23.61. A of t1, okay, where a prime of t is equal to 0 is 21.52. And a of 126 is 62.87. So the maximum acceleration is 62.87 feet per second squared. And the minimum acceleration occurs the smaller of the three numbers at 21.52 feet per second. Okay, so what is it? 32 feet per second squared is the normal gravitational acceleration. So you roughly go 2 g's to maybe 2/3 of the g. Okay, so you'd be floating in one instance and pulling 2 g's at the next instance. That's quite a ride, almost a roller coaster ride. Okay. All right, so this would conclude the lecture for section 4.1. So now you can get started on your WebAssign questions for chapter 4. All right. Okay, so let's see, end of lecture for section 4.1. I'll go ahead and save this one.